The last topic in engineering physics, rotational dynamics, is angular momentum, a concept that Habiba investigated in her IA, and a concept that the elementary school kids really love at that little play park with that spinning merry-go-round. All right, so you can see this video over here on the left where this lady is spinning faster and spinning slower. Okay, what she's doing is she's changing her inertial mass. That's what Habiba was looking at in her IA. And the result of changing her inertial mass caused an increase in her angular velocity. And that's based on the principle of conservation of angular momentum, which we're going to cover a bit later on. But to be able to understand why this is happening, we first need to talk about what angular momentum is. Okay, so here's the formula for what angular momentum is. Okay, the symbol L is angular momentum, I is inertial mass, and that omega is your angular velocity. Okay, and the first thing we'll do is talk about the relationship between angular momentum and linear momentum. So we knew from the first part of mechanics in chapter 2 that linear momentum is equal to mv. Okay, so if I take a point mass and I measure its velocity, that product of that is going to be its linear momentum. So how does that relate to angular momentum? Remember, angular momentum is based on an object rotating in a circle. Okay, so with angular momentum, the formula was L is equal to I omega. Okay, and I represents the inertial mass, which takes the place of m in that relationship, and omega is my angular velocity, which is my relative to my linear velocity. So if I took that divided by r on the left-hand side, okay, I can turn that into omega, all right? And then m has to be converted into the inertial mass. My momentum divided by r probably is going to be related to my angular momentum as well, okay? But it's not as simple because you have to get your inertial mass, okay? So that's the basic relationship between angular momentum and linear momentum. And then when we talk about the relationship between torque and angular momentum, what we have to remember is that the momentum of a system is going to be conserved as long as there's no extra force acted on the system, okay? And force can cause changes in momentum. That was based on the Newton's first and second law, okay? So if I remember that relationship with Newton's second law, Ft is equal to m delta v, that's my change in momentum, okay? Force can be measured as my change in momentum over, I guess, my change in time, okay? And likewise, okay, torque, because torque is the force that causes angular momentum, okay? The sum of my torque can be related to the change in my angular momentum over the change in time, okay? Related to that same formula over there. Okay, so the change in angular momentum over the change in time is going to be equal to torque. Therefore, the sum of the torque times the amount of time that I'm applying that torque is going to be equal to my change in angular momentum. Now that's a pretty important relationship, okay, because then I'll be able to, if I could calculate my change in angular momentum, I might be able to calculate my change in angular velocity, okay? It's a pretty simple way of measuring the change in my angular velocity. Okay, and if I measure the change in my angular velocity, I can measure the change in my angular acceleration, and so on and so on and so on. So I can predict, as long as I'm applying a force to that lady, I can predict what her change in angular velocity be, and how fast she'd be going, how fast she'd be rotating after a certain amount of time applying a torque. Okay, all right, and then conservation of angular momentum. The total angular momentum of a rotating object remains constant if the net torque acting on it is zero. It's the same as conservation of linear momentum. Okay, so as long as there's no external forces, the momentum of the system is going to remain constant. And that's what we're seeing over here. Okay, so what this lady has to begin with, okay, with her arms stretched wide out, let's say that's the momentum, the angular momentum that she begins with. When she pulls her arms in, she's changing her inertial mass. She's changing the radius, r, right, of those weights that were on the outside of her arms, right? And if she lowers her inertial mass, the angular velocity has to compensate. Okay, so when it's out, she's rotating slower. When it's in, she speeds up because the angular velocity has to compensate. So what this looks like is, okay, let's call it I1, angular velocity 1, is equal to I2, angular velocity 2. Okay, there's a couple things I can change. Now, it's hard to change the inertial mass of somebody. Okay, if I change my angular velocity, my inertial mass is going to have to compensate. Okay, or if I change my inertial mass, my angular velocity is going to compensate. And that's what figure skaters do, gymnasts when they're doing flips. There's lots of examples of when somebody's doing a flip, they pull their body in tight, causing them to rotate a lot faster. And that's based on that relationship over there. So that is all equal to a constant, okay, for conservation of angular momentum. So if we want to solve a basic problem, let's imagine that I have a table. Okay, this is kind of related to Habiba's experiment. And I have a string that I can pull. There's a hole in the table, and the string is attached to a mass that is rotating. This is kind of what Habiba was doing. And let's say the initial radius was, or not, the doesn't really, yeah, okay, let's say the initial radius, let's say is 0.8 meters, okay? And then I pull the string so that the final radius is 0.4 meters, okay? And using that system, how I want to be able to calculate the change in my angular velocity as a result of that, okay? So what I'll need to do is I'll need to know the inertial mass of the system prior times the angular velocity prior, and then I'll create that relationship over there. Okay, now for a system like this where it's an object swinging like that, it's like a hoop. So mr squared, okay, times omega 1 is equal to mr squared, let's call this r1 and r2, times omega 2. I can see that the masses cancel out. All right, so if I wanted to find, for example, my new velocity as a result of pulling that radius in to half what it was, okay, then I would just do this. I would move r2 over, so the r1 squared over r2 squared times omega 1 is equal to omega 2. Okay, and what we can see is that if 0.8 squared divided by 0.4 squared times whatever my initial angular velocity would be my new angular velocity. You can see that it's going to speed up quite faster, okay? And that would be how I would be able to solve that. Another interesting property of angular momentum is that it's a vector quantity. So if you started spinning a disk around in a circle, the faster you spin it, the more angular momentum it has. The angular momentum has a vector that is perpendicular to that spin. It's related to the axis of rotation, and it follows the right-hand rule. So if these fingers are the direction of the rotation, the angular momentum vector is straight up. Okay, now because it's a vector, if I'm going to change the vector, if I'm going to start tilting that rotating disk, I'm going to have to apply a force because I'm changing the vector, right? So remember, like circular motion or centripetal force, when you're changing a vector, it's going to create a force, okay? So you're going to have to apply force to change that vector. So when you have a spinning disk rotating really fast, it's actually quite hard to change its axis of rotation, okay? That's, for example, if a tire falls off a car on the N1 in Accra, okay? It's going to keep rolling. It's not going to start tipping over to its side because that tire has incredible angular momentum. It'll take a lot of energy to make it to tip. It'll have to slow down before it tips, okay? So here's an example of a demonstration that you would often see, okay, for a conservation of angular momentum. The physics teacher is making that bicycle wheel spin, okay, and right now the vector is this way, okay? So if this person applies a torque and changes that vector, it's going to create a resultant force, a reaction force, that's going to cause the person to start to move, okay? And you can see he created a reaction force that is pushing him and making him move. It's applying a torque. The spinning wheel is applying a torque to the guy sitting on that chair. Okay, and that's kind of how like gyroscopes work. Okay, so here's a good example as well of an invention you guys know of, a spinning top. When you spin it, it doesn't tip over because there's angular momentum, and it'll only start to tip over when it slows down so that gravity can act on it. All right.